Tissue engineering is a multidisciplinary field that combines principles of engineering and life sciences to create functional biological tissue. The goal of this project is to design a surgical micropuncture device for new blood vessel formation. The sponsors of this project are Dr. Ravnik and Dr. Lewis from PSU College of Medicine and Penn State. The method of new blood vessel formation is called angiogenesis and is currently being performed by using a 60 micrometer needle to make punctures along a rat femoral artery as shown. As seen, this process is inconvenient, time-consuming, and the precision rate is very low.
Our device has to be safe, stable, precise, affordable, sterilizable, and/or disposable. For the first prototype, we came up with a plier-like design. The design was chunky, uncomfortable, and required 2 hands to operate. As seen, this process is clearly not optimal for microsurgeries. Here you can see our final prototype with all the edits. It is way thinner and smaller. This helps with comfort and ease of use, as well as the ability to use with one hand, which makes it more precise. This is a close-up view of how the needles are stored in the device. Here you can see the steps we took to build the disposable needle cartridges. We started with CAD designs and 3D printed the molds in flexible resin. We then placed the needles inside the mold under the microscope and filled the molds with epoxy to create the final cartridge. That is inserted into the device as seen.
We did 3 different tests, focused on time, precision, and proof of puncture. We punctured 0.8 millimeter diameter plastic tubing and ran water through it to test if the needles punctured through successfully. As seen, the water leaked through the holes made by the device.
For time testing, we used angel hair pasta to mimic a real vessel. This clip shows us using the old method of puncturing with needles, which took us 60 seconds. While using our device, it only took 10 seconds.
We used 5 millimeter diameter plastic tubing, which made the punctures easier to see. We measured the horizontal and vertical lengths of the distance between each puncture and found that the relative percent error was reduced significantly when using our device compared to puncturing manually. In conclusion, we were able to prove that using our device is more precise, fast, and efficient. Our future plans involve 3D printing the device in stainless steel and replacing the press-fit dowel to secure the device together. Finally, we want to begin testing our device on animals to further study our design and release it into the market for clinical use.